Okay, some more circular motion problems. In this case, what we're going to do is we're going to take a look at going down a hill, and we're going to take a look at the force supplied by the track at the bottom of the hill. And then at the top of the hill, we're going to look at what's the uh, maximum speed that this roller coaster car can go over this part of the hill without like leaving the track, without launching itself. So let's take a look at this. We've got part A. Well, let's read the whole thing. I've got a 526 kilogram roller coaster car that rolls past A at the bottom of the hill and then past B at the top of the hill. And we want to know if the vehicle, if the roller coaster car has a speed of 29 meters per second at the base of the hill, what is the force of the track on the vehicle at this point? That would be the normal force. To show you that this is indeed the normal force, let's take a look at a force diagram for the roller coaster car at point A. So at point A, here's my roller coaster car. I've got two forces acting on the object at this spot. First is weight, of course, which is equal to the mass, 526 kilograms times 9.8 meters per second. Squared. And then we've also got, since it's sitting on a surface, the track, we've got a normal force. Let's go ahead and calculate that weight force. So we've got 526 times 9.8, and that's going to be 5,155 newtons. Now it would be great if it were easy, that the normal force and the weight force would be equal to each other, but that's not the case here because this object is accelerating. It's got centripetal acceleration as it goes through this curve at the bottom of the hill. So in that case, what we have to do is apply Newton's second law, which is sum of the forces is equal to mass times acceleration. And in this case, since it's accelerating in a circular path, it's going to be acceleration centripetal. So the sum of the forces, I've got my two forces here, which is F normal plus negative Fg, because it's pointing downward, is going to be equal to m centripetal acceleration, m times the centripetal acceleration. We know the force of weight. We're trying to find the normal force. We know the mass. The only thing we don't have is the centripetal acceleration. So we're going to calculate that using acceleration centripetal is equal to v squared over r, which is 29.0 meters per second squared over the radius of that curve, which is 10 meters. So we've got 29 squared. That's going to be 8.41. meters per second squared. You know what? Let me show you real quick how I got that. I squared 29. That's 841. I know I'm going to divide by 10, so I just moved the decimal place over. Oh, it would be 84.1. Boy, I'm glad I checked that because that would have been dumb on my part. All right, let's fix that. 8.41. No, 84.1. There we go. All right. So we've got the centripetal acceleration. We can now figure out the normal force. So let's take a look at this. And that's going to be F normal is, F normal plus a negative 5155 newtons is going to be equal to 526 times 84.1. So that's going to be, force of normal is going to be equal to, let's go 526 times 84.1. And it's going to be 44,237. So it's going to be 44,237 newtons plus 5,155. I'm going to add 5,155 to both sides. So I get the normal force, which is the force supplied by the track. As we can see that would be that normal force from the surface. It's going to be 49 something. So let's add 5155. And we get 49,392. 49,392 newtons is the answer. At the top of the hill, what's happening is we're going to the top of the hill, and if you think about when you're sitting in a roller coaster, when you get to the top of the hill, you barely feel like you're sitting in the seat. You're coming out of the seat because there is no normal force. Over here at the bottom of a roller coaster hill, you feel like really heavy because the normal force that track is pushing up on you to keep you from continuing on in a straight line and down this way. Well, in this case, there is no normal force. So let's go ahead and draw a force diagram for this. Here's my roller coaster car at the top of the track. Like I said, you're going up over the hill and you don't feel like you're in the seat because the normal force basically disappears as you go over the hill. So all we've got is the force of weight, which we've already figured out as 5155 newtons. We're going to apply the same stuff that we did before. We're going to have the sum of the forces is equal to mass times acceleration centripetal. Let's go ahead and figure out that centripetal acceleration because it's different because I've got a 15-meter radius this time. So acceleration centripetal is going to be equal to, v squared over r. That's what we're looking for. We're trying to find this velocity, right? It says what is the maximum speed the vehicle can have for gravity to hold it on the track. So let's back this up a second here. Let's go ahead and, what do I want to do here? Oh, I know what we need to do. We're going to need to figure out this centripetal acceleration and use that to solve for velocity. We've got the only force that is acting on this object, on the roller coaster car, and that's weight. So we've got 5155 newtons is going to be equal to that 526 kilograms times acceleration centripetal. Well, that means that that acceleration is going to be equal to 5155 newtons divided by 526 kilograms, which is equal to, let's see here, let's clear that. 5155 divided by 526 is equal to, look at that, 9.8. 9.8 meters per second squared. That's going to be true of any roller coaster as we're going over the hill. If we're looking for that maximum speed, the fastest we can take that hill at without launching this thing off the track, that would be for a car going over a hill in like San Francisco or whatever. It's always going to be gravity, 9.8. So let's go ahead and we can now use that 9.8 meters per second squared is going to be equal to v squared over r. R is 15 meters. So v is going to be equal to the square root of 9.8 times 15, which is going to be equal to 1212, I believe. 9.8 times 15, and then we're going to square root the answer, and we get 12.12. Yeah, 1.12 meters per second. Another way to look at this, when we took a look at a loop-the-loop problem, we calculated, by using the variables that on the inside of the loop, at the top, the only acceleration is due to gravity. This time we're just on the outside of the loop. It's the same kind of concept.